So the beam is simply supported and loaded as shown. The beam is made of 3 plates with 2 joints, joint A and B. First of all, the cross section of the beam is an I section. And when they say that there are 3 plates, it's these plates. So there is the vertical plate and 2 horizontal plates. And those horizontal plates have to be joined with the vertical plates through joints A and B. The width of the beam is 20 millimeters. Okay, I guess that's what they mean here. And the location center of the section is at C. So the center is given. The moment of inertia is also given. Find the average shearing stress at joint A and joint B at section NN. Okay, so since we asked for the shear stress, we know the formula for the shear stress is V Q divided by I times B. And in this case, we want the shear stress at NN, or sorry, joint A and B, but it's at section NN. So we need to find V at NN, right? So once we have V at the section NN, we can put that V in there. And then we need to find the other things in this equation to solve for the shear stress. So the first thing to do here is to find the shear stress at the section NN. So this is where we go back and look at the bending moment or the shear force moment diagram. In this case, you really don't need to draw the shear force diagram. You just need the shear force at NN. So I'll just find the shear force at NN. But before I do that, I need to find the reactions at A and B. So I need to do the free body diagram. So let's draw the free body diagram. Okay. And since we're interested in shear force, well, first of all, Fx, where x is this direction, y is upwards, is going to give me HA equals 0. It's not very important here. Nevertheless, we'll just find it. Fy equals 0 gives me VA plus VB minus 1.5 minus 1.5, but the external forces equals 0, which means that VA plus VB is 3. Okay, the last step is to use the moment equations. So this distance seems to be 0.4, 0.4, 0.2. Okay, so let's use the moment equation. You can choose point A, point B, whichever you want to. You can choose some other point too. There's more benefit in choosing A and B because the moments, so the forces will disappear in the moment equation. So let's just choose A. So that equals 0. So we have 1.5 acting at a distance of 0.4 from A. And since it has a moment which will turn the beam clockwise about point A, just when that force 1.5 acts, we'll put a negative sign because clockwise negative. Then we have 1.5 acting at a distance of 0.4 and 0.2. So you need to add them, so 0.6. And it also produces a clockwise moment. And then we have VB, which is acting at a distance of 0.4 plus 0.2 plus 0.4, which is, I think, 1 meter. And then that produces a counterclockwise moment, so it's positive. All that equals 0. And so solving for VB, it's just 1.5. It's 1.5. Okay, which means VA is also 1.5. Okay, so it's not, well, it's not actually surprising. I didn't notice this, but this is what is commonly known as a 4-point bending, uh, 4-point bending loads, which means that if you draw the bending moment diagram, you'll see that the bending moment is constant from that 1.5 on the left to 1.5 on the right. One of the diagrams I drew earlier. And this doesn't come as a surprise, actually. We could have found this by inspection. We didn't have to do all the math. Okay, so so with that, let's just find the shear force at NN, right? Any section between A and 1.5 force. Now, this is where we look at the shear force diagram equation. We did this shear force. Okay, I'm not going to draw the whole thing, but I'm just going to draw that figure, which will help us to find the shear force at NN. So you can start from the left or right. So if you start from the left, you're going to put the force, which are the external forces, which is 1.5. So let's just write 1.5. And then put V downwards, where downwards is positive by a sign convention. And if you want movement, it's going to be positive counterclockwise, and then write the equation. So positive V, because the convention is downwards is positive for shear force diagram, okay, not for the other things, which is the free body diagram. Minus 1.5 upwards is negative equals 0. And so we see that V is, that is at NN, we just said as V is 1.5. So it's 1.5 kilonewton. Okay, that was what we're after. Now, I did a lot of math here. This particular problem, it's actually kind of easy. So if you see something like this, if you write down 1.5, just explain why you got 1.5. It's basically a symmetric system, and you can easily get 1.5 without having to do all this math. That's absolutely fine. Okay, question? Okay, so we got that. Now let's go to the shear force equation. Okay, we said shear force is VQ divided by I times B. And let's do this computation for joint A and then do it for joint B. So shear force for joint A. So I'm just going to isolate the top part of the beam, because remember when we talked about shear force, it's always that you find it for the section above the point you're considering. So if joint A, then the shear force occurs because of the thing which is above point A. So it's only going to be due to the top plate. So I draw the top plate. I'll show the centroid, which is also the neutral axis. That's my C. That's the joint A. We call that A. Let me put some dimensions there. So from the figure, which is now on the previous page, this was 0.1. The thickness was 0.02, was 20 millimeters. And then I need to find, the centroid of this. And that centroid is because I need, when I compute Q, it is Y dA for, it will be Y1 and C. So Y1 to C. That integral is actually can also be, well, you could actually do that integral by taking a small element integrating, or this thing is actually also equal to the centroid from, so let's call that Y1, from the neutral axis times the area, and the area is, this is the area. So I need to find the centroid. So the centroid from the neutral axis is, we go back, Okay, let's find the centroid, this distance. Okay, so this is 80 plus 20. This whole thing is 100, but then this is 68.3. So it has to be that this part is 100 minus 68.3. 80 plus 20 is the distance from here to here, and then minus 68.3. 8.3. Yeah, I'm just trying to use this to my advantage. But yeah, you could do it that way too. You could take 110, in which case, if you want to do 110, it'll be 110. So yeah, that's a better idea. So if you want to do, if you want to find y1, a better way to do it is to probably take it this way. So just find the centroid, which is this distance. So that will be 110 minus 68.3 will give you y1. So you don't have to do more work. So y1 bar, let's call it, equals 110 minus 68.3. It's 41.7. Let's just use 41.7 there. Okay, so 0.417. Right now, that's 0.417 meters. So it's 41.7 millimeters divided by 1,000. Okay, so that's that. The area is, that's just 0.02 times 0.1, right? Okay, so we got that. Now we need to figure out the inertia. So inertia for this section is something which we will give you. It's basically hold on. So the inertia for this thing, you will actually have to find it about this axis. So it will be the inertia of this thing about the centroid, plus then you need to use the parallel axis theorem to find inertia about C. It so happens that in this case, you're given the inertia. It's given as 8.63 times 10 raised to negative 6. So I just use that. 8.63 times 10 raised to negative 6 meter raised to 4, or meter raised to 4, yeah. And thickness, or B in this case, is, well, let's go and look at what B is. So B is the width, right? It's the width in the side view. So let's see if there's something similar here. Okay, it's the distance in this direction. It's given as 20. So 20 millimeters. Okay, so using all this, we have shear stress at joint A equals V, which is 1.5 times 10 raised to 3 times Q, which is 0.02 times 0.01. So that's the area. And then we have 0.0417. Just working on it. Just call that tau A. 0.0417. So area y1 bar phi divided by, oh, it's a bad place to do it. I'll write it on top. So that divided by I, which is 8.63 times -6 times B. Okay, so that comes out to be 7. Yeah, I was given. And this is also given. Okay, so we need to do the same thing for B. Shear force at joint B. So let's just draw B. You know what? Why don't I give you the final answer and then you try to work it out yourself home? I'll fill the dots. I'll post the solution, but I would like you to try it yourself. So all you need to do is do the same math I did, except that you will look at joint B. So if you do everything right, you'll get shear stress of 608 kPa. Okay, so I'll fill the dots and post it. So shear stress, but I would like you to try it out yourself. Yeah. Yeah, question. Uh, that's what is given. It's the inertia. It should be the same. It's sorry, it's the inertia of the combined thing. My bad. In terms of, so when you look at the moment of inertia for the bending moment, it's the inertia of that particular section. So it will be, so if there were M involved here and we're trying to find the normal stress, it will be the inertia of that horizontal section. For the shear force, it's the inertia of the complete system, which is in that formula. Because it's slightly different setup. It's not the integral in this case is so this integral is for the cross section area, but this integral, this inertia is the complete inertia. And we can trace back where it comes from. Closed it by mistake. Okay, let's trace it back. It comes from this formula. Interesting. Okay, so my bad. So it is to be computed like the inertia you compute for the moment. My belief is that if you do the computation for this particular cross section, the difference in area is going to be insignificant. So it's probably that the vertical part dominates the cross section, and the calculation won't give you a huge difference. That is, because of the inertia, the calculation won't change. That's my hunch. But yeah, you need to, the inertia which we get over here comes from the moment equation. So it is to be computed exactly the same way you compute the inertia for the moment calculation. So that's a good question. The second problem, there was a question about this problem, and the question is to do with this width, 20 mm. Right. So the question is, well, what is the shear stress at joint A and B? A is here, B is here. And then when we solve this, there's this formula, right, which basically gives the shear stress is the shear force V, Q is the first moment, I is the second moment, and B is the width. And the question says use 20 mm, but where's this 20 mm coming from? It's basically this. What is 20 mm? So when joint A shears, it'll shear across this surface, right? And we really have we have two choices. We can use 20 mm, which is this, or we could use 100 mm, which is just above it. And you can see from this formula that the smaller the B, the bigger the shear stress, and you want to use the worst case shear stress. So you would use P equals 20 mm, which is this width, to solve for the shear stress. Okay. That's what it was used. And then that part I'll complete in case you've not done it. Okay. So we are solving this problem now. And it's a more of a design flavored problem. So you can expect this is where we're trying to get to in this course, where we're trying to find unknowns in terms of dimensions such that they meet certain shear stress or normal stress criteria. Okay, so let's read through it again. A beam AB supports 3 loads. The material used for the beam has a normal stress of 1800 psi and shear stress 120 psi. Okay, which is a material property. So you don't want to exceed those stresses. If you exceed, then this material will fail. Determine the minimum depth D, so which is over here, such that it meets the strength constraints specified by the given stresses. So these are the constraints. So for a problem like this, which is a design problem, there are really 2 criteria, right? There is a maximum normal stress, the maximum shear stress, which don't need to be exceeded. We know what the shear stress is and the normal stress is, which came from the previous 2 sections. So what we'll do is we'll basically design D based on one of the 2 criteria, that is sigma, say, and then find if that corresponding shear stress is exceeded or not. If it's exceeded, then we change our criteria and redesign it. That's how these problems are done. But before we do that, one thing to remember is things fail when something reaches its maximum value. So in this beam, you need to find the first thing you need to do is find the maximum M and maximum V, because those M and V will figure out in the formula for sigma and tau. Okay, so this is what we're going to do. Find max V and max M, okay, which means that we need to probably do the shear force and bending moment diagram, because that will tell us precisely which point will have the maximum V and M. The second step is assume so use sigma max to design for D. Okay, that's the criteria. And then check tau max is, tau is less than tau max. Okay, if now one of the two things can happen. One is it will fail this criteria, or it will meet this criteria. If it fails or meet, you want to do the third step, which is, so if it fails, then clear, you need to change your criteria. Okay, so we use the maximum shear to design for D, and then we'll check sigma is less than sigma max. So if it satisfies criteria 2, we just stop. If it doesn't satisfy 2, we go to 3, and that's where we stop. You could change the order. You could do 3 instead of 2. That's absolutely fine. Okay, this problem will have only one answer, irrespective of how you do it. 1, 2, 3, or 1, 3, 2. So do either. Okay, so I should put here if tau less than tau max fails, go to 3. Okay, and then another note is that you could reverse. You can reverse the order of 2 and 3. Okay, you'll get the same answer. Okay, so step 1, shear force and bending moment diagram. Let's do that first. So I'll redraw that figure and then draw the shear force and bending moment diagram. Step 1, let's call that 1A, reaction forces, right? Before you do shear force and bending moment diagram, you need the reaction forces. So let's draw the beam. And I'm assuming that, well, it's not clear here. I'm assuming that the way this is set, it's basically transmitting, it's sort of on rollers. So there's only a vertical force that it needs to bear, and there's no horizontal force and no moment. Okay. So let's assume it's to be, let's call that V1, V2, and then there are 3 forces, 2.5, 1, and 2.5. The distances are through 3, 2. I mean, let's just try it a little bit differently so that the spacing is a little bit more representative of the distance. So let's draw this one closer, this one a little further away, further away. So is that right? I drew not too many forces. My bad. I'm sorry. So 2, 3, 2, 2, 3, 3. Okay, so summation of forces in the y direction is 0. So V1 plus V2 upwards is positive. Minus 2.5 minus 1 minus 2.5 is 0. So we have V1 plus V2 is 6. And then we can take moments about any point. Let's take it about, say, A. So we would have 2.5 times 2 is going to be, so the force 2.5 will induce a clockwise moment about A. So we put a negative sign. Similarly, 1 times 5 will have a clockwise moment. And then 2.5 times the distance is 3 plus 2, 8. We'll also have a clockwise moment. And then V2 with a distance of 3, 6, and 4, so 10. And that will induce a counterclockwise movement, so plus. Okay, and I will just write down what I got. Solving for V2, we get 3, which means that V1 is also 3 because the sum is 6. So that's the first step. Okay, now there's a shear force and bending moment diagram. So let's do that. So 3, 2.5, 1, 2.5, 3. So let's draw the shear force diagram first. Okay, now this itself is an exercise, right? So I will do it a little faster than I normally do, right? Take a section, cut it, write the equation for shear force and so on. This one is actually pretty simple. You can do it by inspection. So when you cut the section here, okay, we would have a shear force of, well, it'll be 3, right? So some force over here has to balance this 3. And the convention is, since this V is downwards, we'll have to do 3 minus V equals 0. So V will be positive. So 3. So it's 3 up till here. Right when it reaches this 2.5, the effect of 2.5 downwards is going to decrease the shear force by a factor of 2.5. So 3 minus 2.5 is what I'll have over here. So it'll drop down. That's 0.5. Let's draw big, slightly bigger. So that's 3. 3 and then drops down to 0.5. And then as you go here, since this effect is again in the same direction downwards, it's going to change that 0.5 minus 1 will be minus 0.5. So it drops down further. Here it keeps going. But then when it reaches here, again 2.5, an effect of decreasing the shear force, right? So 2.5 minus 2.5 minus 0.5, so it'll be minus 3. And then once you reach here, there's a 3 downwards, but then there's 3 upwards. And so the shear force is going to be 0. So this is the shear force diagram we got just by reasoning out, just reasoning out without actually writing any equations. Okay, the bending moment diagram. It's all positive, so I'll just try it this way. Okay, so for bending moment, which I think is even more harder than the shear force diagram, what you do is you take a section and you assume that sagging, sorry, counterclockwise is positive, and then you write the equation and do it. Another way, and there are many ways to do it. Another way to do it, do this bending moment diagram, is to notice that, see, Tm, sorry, tvdx is m. Is that right? Is that right? Somehow I'm blanking on this basic formula. Can anybody who remembers this correct me if I'm made a mistake? It's opposite. Yeah, it should be mdx doesn't have the units of, so this doesn't have units of m, so it has to be the opposite. It has to be, okay, now the units make sense. Moment has units of force times distance, so the distance divided by distance gives you the force, and that should be the, thanks. Okay, so this, from this formula, I can see that m, so dm integral equals v dx. So moment from, let's say, one point to another point is simply integral v dx from those 2 points, so 0 to 1. This is basically area under vx curve. That's how you compute the area. So we can actually use the area under vx to figure out what is the change in moment, and that's what we'll be using. So for this particular thing, for the problem is actually kind of simple. The area, this area is, well, you can observe that it is 3 times. 3 is the height, and the distance is 2. So 2, 3, 3, 2. The area is 6. And then the area over here is going to be 0.5, which is the height, times the width. So 3 times 0.5 is 1.5. And then the area here is minus 1.5, just because the coordinate is negative. And then area here is minus 6. Okay, so what we can do now is we can use this fact to find the shear force diagram kind of faster without actually using any equations. Okay, so the bending moment, only we need to know is the bending moment at 1 point, and then we can just keep using this. So bending moment here is 0, because you can see there's no bending moment there. And then to find the bending moment at 1, which is, let's say, at this point, is going to be, so this is 0, this is 1, so then it will be m1 minus m0 equals the area under the curve, so 6. But this is 0, so m1 has to be 6. So this has to be 6. Now the question is, how do you connect 0 and 6? Whenever the force is constant, like as we see here, the shear force is constant, the bending moment is simply going to be the force times distance. But since the force is constant, it's going to be a linear function of the distance. So we can confidently say that this has to be a straight line. And that's only because there is a force and not a distributed load. Yeah, question? Shouldn't be 5.
3 times 2, carry under the verb. So it's 2.5 and 1.
No, it's the whole, the complete
That's
area.
the force, not the. Oh.
Yeah, this is the force. So it's this 3 times 2. This is 2. This is 3. This is 3. This is 2. So look at this and this area of the rectangle, and then again area of this rectangle. in the area of that rectangle and so on. Okay. So that's 6. Now go to the next point. That is, if this is 1 and this point is 2, then we can say that m2 minus m1 equals the area under this curve, or area under that rectangle is 1.5. But m1 is 6. That's 6. So m2 has to be 6 plus 1.5, so it's 7.5.
Wait.
Yeah, it's just this formula. Maybe I write it here properly. Okay, so this is m1, this is m0, this is m2. Okay, m2 minus m1 equals area under the curve, this area, which is 1.5. So m2 minus m1 is 6. This is 6 equals 1.5. So 6. So m2 equals 7.5. Right? Just move this to a different page. Okay, so we can keep doing that, which is, this is m2. And by the way, I drew a straight line between m1 and m2 just because it's a constant force. For a constant force, a straight line. If it was a distributed load, then it will be a quadratic curve. You have to draw it with a curve. So second order. So let's just do that for the next one. So m2, we need to find the moment here, m3. So m3 minus m2 equals v dx, but v dx is the area here, which is now negative. So m3 minus m2, m2 is, we found it to be 7.5 equals minus 1.5, and so m3 is 6. So it comes back to 6. And then if you compute it over here, you'll see it'll be 6 minus this 6, it'll be 0. And you can use the formula too. So that's the bending moment diagram, and we got it without using the equations. If you like this, feel free to use it in the exam or otherwise. It's a neat method of solving for the shear force bending moment. It's a little bit harder when you look at distributed load. You can try solving problems both ways and seeing the answer. Okay, so we got that. What we were after here was, we want to find the maximum V, right? Because that's the place where it will fail in shear. And we can say the maximum V is here or there. So there's a high chance that this beam will fail either here or here when the maximum shear stress is reached. So we only need the value. So it's 3. See if the unit size skip. Yeah, it skips. Okay, and then the maximum moment, all you need to do, look at the shear force diagram. We see that 7.5, and it occurs right here. V max, and then the shear force is just going to occur right here. M max, right there. So that's 7.5. So we just need that value. and the units are going to be kip. The length was in, it's in feet. So since we used feet for the length, this will be kip feet. Okay. Now what we'll do is, let's see, I believe that the dimensions are in inches, right? So let's just convert everything into IPS system. So let's get rid of the feet. So let's convert that to kip. So if you want to convert feet to inches, we need to multiply by 12, right? 1 foot is 12 inches. So multiply by 12, and we get kip inches. And I'm only doing that because the dimensions were in inches. So it was 3.5 inch, right? Remember? Okay, so that comes out to be 90 kip inch, or 90 times 10 raised to 3 lb force inch. You could also convert that to lb 3 times 1000, so 3000 lbf. Okay, so we are now ready to solve for the diameter. Okay, we need to find this diameter. So step 2 is to assume that the beam fails when the normal stress is exceeded, that is exactly midway where M is max, and use those formulas to find the D. So second step, assuming use normal stress for design. So in this case, M max is Rm, which is 90 times 10 raised to 3 lbf inch. Okay, so this is our cross section. There's D, which is unknown, and then there is 3.5. So if you recollect, the normal stress is sigma equals M times Y divided by I, where Y is this distance from the neutral axis. Okay, so if you want to figure out where it fails, it actually would fail at the topmost surface, because the shear stress, the normal stress, sorry, is 0 in the neutral axis, because when you put y equals 0, it's 0, and then it achieves maximum at the extreme value. So sigma equals M. So for y, I'll put D divided by 2, and then inertia is 3.5, so it's 1/12 times 3.5 times D cube. Okay, that's always the inertia. So this is B, and this is D. Then I is 1/12 B T cube. Okay, you will be given this particular formula. Okay, so sigma is, now what's sigma? Well, we'll use, since we're assuming that it's going to, if it fails, it will fail when this limit is achieved. We need to put the maximum value, sorry, the strength, the normal stress corresponding to the strength. So in this case, it is 1800 psi, 1800 psi. So M is 90 times 10 raised to 3. D is unknown. 112, 3.5, d cube equals 1800. And so you eventually get a quadratic equation. There's a d square, but that's not too hard because you just have to take the square root of everything when you simplify there. And if you compute the diameter, it comes out to be, or sorry, the width, sorry, the depth, then you get 9.258. In checking on this, I got 6 times 90 times 10 raised to 3, 3.5 times 1800, and that comes out to be 9.258 inch. Okay, so far so good. We've got D. Now the second step is to verify if the shear stress criterion is met. Which is the tau max should not be exceeded. So what we do here is for this section, that is a rectangular section, we know the formula for the shear stress. It's 3 divided by 2 V divided by A. So what we do is we put the maximum value for V, and I think I believe I have it on the previous page. It's 3000 lbf. So we put 3000. So 3000. The area is going to be, it's B times D, but we've computed what D is. It's 9.258. So it's 3.5 times 9.258. And this comes out to be 138.8 psi. However, the max is 120 psi. So we are given that the maximum shear stress that the material can bear is 120 psi. Unfortunately, 138.8 psi is greater than 120 psi, and hence we can be certain that this material will fail in shear if we design it with a diameter or a depth of, say, height of 9.258. So it does not. Shear stress criterion or criteria. So does not meet specs, right? Okay. So we reverse our criteria. We first design based on shear stress and then check the normal stress. So let's do that. So that's step 3. Design using shear stress. So now we know that it's 3 divided by 2 times V divided by A. And so tau is given as 120, which is now going to be our design criteria. 3 divided by 2. V is 3000. And the cross-sectional area is, well, it's 3.5 and D. So 3.5 times D. So it's fairly easy to solve for D. It comes out to be 10.714. So it's very interesting that the T has increased. So then we can verify with the normal stress. So that's sigma max. So we know now that sigma is my divided by I. Again, sigma would be max when m is max and y is max. Y is max when it's at d divided by 2. So m is max at 7.5 times. I mean, I converted that to IPS, so it's going to be 9t times 10 raised to 3, and then y is d divided by 2, and then I is 1/12 b d cubed. So b is 3.5 d cubed. So, but now d can be substituted as 10.714. So 10.714 divided by 2 and 1/12, 3.5. Okay, so just plugging in the numbers, get 1, 3, 4, 4 PSI. Okay, which is, by the way, less than 1800 PSI. It is a question. Where does 3 by 2 V divided by A come from? Okay, good question. So this is from our notes. Okay, so from our notes, the formula for shear stress is tau equals 3V divided by 2A and all those things. But we notice that the maximum shear stress occurs when Y1 is equal to 0. And so we're left with 3V divided by 2A. So that's where the maximum shear stress comes from, which we're now using in here. So this meets the criteria, or this meets the criteria. By that I mean it doesn't fail in shear, in normal stress. So our design, so final design is D equals 10.71. Okay. So that question took me the whole class, but that's the kind of things you are expected to do. And in particularly when you're doing senior design, something like this is valuable. If you're designing something where its ability to bear certain stresses is important.